So we will be talking about one of the compound events, which is known as the mutually exclusive event under theoretical probability. So what is an mutually exclusive event? So mutually exclusive events are events that cannot happen at the same time. So from the word itself, exclusive. So just like having day and night at the same time, that cannot happen. Being strong and being weak, feeling hotness and coldness, or going down and going up. These are exclusive events. So we cannot have this at the same time. But if we can have the events happening at the same time, we call it not mutually exclusive event. Events that can happen at the same time. Just like singing and playing instrument, we can do this at the same time. Singing and dancing, we can do this at the same time. Uh, Having the computer and texting, we can do this at the same time. So once the event can happen at the same time, we call it not mutually exclusive event. So whenever that we are going to compute for the probability of such event, so if the event is categorized under mutually exclusive event, so the probability of A or B will be equal to the probability of A plus the probability of B. But if the event is not mutually exclusive, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, meaning the probability that the event happening at the same time. So let us have a couple of examples for us to understand what this event is all about. Example, we are having an experiment and we are to roll a regular die. So a regular die, as we all know, consists of dots having the numbers from 1 to 6. So meaning the total number of possible outcomes whenever that we are rolling a die is 6. So this 6 will serve as our denominator. So let's have the first one. The probability of getting 5 or an even number. Probability of getting number 5 is just only 1. And the probability of getting an even number, talking about the numbers 1 to 6 present on a die, are the numbers 2, 4, and 6. So these are the numbers present on a die. So therefore, the first probability or the first event has a probability of 1 over 6. So this over 6 is based on the total number of possible outcomes, which is this one. While for the second event, probability of getting even numbers, so we can state that we do have 3 over 6 as the probability for this one, since we do have 3 elements under even numbers. So upon looking at the elements that we do have from the first event and the second event, we don't have common elements, meaning this number 1, this event in number 1 is under mutually exclusive event. So we're not going to have any subtracting value here. So to finalize our answer, we just simply add these two. So we do have 1 over 6 plus 3 over 6. So this gives us 4 over 6. Or we can further simplify this as 2 over 3. So that is how we determine the probability of mutually exclusive event. Let's have the next one. Probability of getting odd number or an even number. The first event of getting odd number are the numbers 1, 3, and 5. So these are the odd numbers. While for the second event, getting even numbers, so just like the first one, we do have the elements or the numbers 2, 4, and 6. So therefore, the probability from the first event, getting odd number, is 3 over 6. While for the second event of getting even number, we do have 3 over 6 as well. Upon looking at the elements of first event and second event, or set A and set B, we don't have common elements again. So meaning this event in number 2 is under mutually exclusive event as well. So no subtracting value. We just simply add these two. So 3 over 6 plus 3 over 6. So 3 plus 3, that gives us 6. So we copy the denominator 6 since we are dealing with similar fractions. And 6 divided by 6, therefore, our final answer is 1. So hope you understand. Let's have another example. Still dealing with rolling a regular die. Third probability is getting prime number or composite number. First, what are prime numbers? So prime numbers are numbers that have a single distinct factors. So what are those numbers that are considered prime number from numbers 1 to 6? Those are the numbers 2, 3, and 5. Because we cannot factor 2 more than one kind. No? So we do have 2, just only 1 times 2, no more no less. Same as 3, only 1 times 3, or 3 times 1, just only one pair. For number 5, we only have 1 times 5 only, no other pair. So that's why these numbers are considered prime numbers. While for the composite numbers, these are numbers that can be factored more than one pair. So therefore, in a die, we do have the numbers 4 and 6. Why are these numbers considered composite numbers? 4 can be factored using 1 times 4 or can have 2 times 2. So that's why it is a composite number. Number 6 can be factored more than once as well. We can have 1 times 6 or 6 times 1, or rather 3 times 2. So that's why 4 and 6 are under composite numbers. So therefore, the first event getting prime number is 3 over 6, while the second event getting a composite number is 2 over 6. Looking at the elements that we do have from our set, nothing is the same. They are not sharing any element. Therefore, number 3 is also under mutually exclusive event. So no subtracting value. So we now add this 2. So 3 plus 2, that gives us 5. So over 6, since we are dealing with similar fractions. So we can further simplify this. So this will serve as our final answer. Another example. Number 4, probability of getting a number greater than 3 or divisible by 3. So the first event is getting a number greater than 3. So therefore, those numbers from our first event are the numbers 4, 5, and 6. So we cannot include 7 and so on because we are plainly dealing with the numbers 1 and 6 because we are talking about regular die only. While for the numbers divisible by 3, these are the numbers 3 and 6. So no more, no less. Therefore, the first event do have the probability of 3 over 6. While for the second event, it has a probability of 2, since we have 2 elements, so 2 over 6. Upon looking at the elements from each set, we notice that both of these do contains number 6. Since they do have number 6 on both sets, therefore we are going to have a subtracting value. Meaning, our probability in number 4, the event that we do have in number 4, is under not mutually exclusive because the number 6 is not exclusive to one another. Both of them are sharing number 6. Since there is only one common element between the two sets, so we are going to have subtract minus 1 over 6 only. Since there's only one common element. So we now simplify 3 over 6, so we add 2 over 6, then 1 minus 6. So this is based on the formula under not mutually exclusive event. So we add the probability of the two events, then subtracting the common elements or the event can happen at the same time. So 3 plus 2 is 5 minus 1, so that gives us 4. So 4 over 6, or we may further simplify this as 2/3. More example, let us have fifth example. Number 5. Probability of getting prime number or less than 5. The first event is getting prime number. Again, prime numbers are numbers that can be factored in a single pair. Two distinct numbers only. Single pair of factors. So, therefore, we do have the numbers 2, 3, and 5 again. While for the second event, less than 5, so the numbers that are less than 5 are the numbers 1, 2, 3, and 4. So, the first event do have a probability of 3 over 6, while the second event do have a probability of 4 over 6. Looking at the elements from each sets, we notice that both of these sets do contains number 2 and number 3, 2 and 3. Since there are two numbers that are present on each set, so we're going to have minus 2 over 6. So that makes this event under not mutually exclusive. So we may now simplify this. So 3 plus 4 is 7 minus 2, so that gives us 5. Copy the denominator over 6. So no simplest form. So this will serve as our final answer. Number 6 example. So this is the last one for this experiment. Getting a number greater than 5 or less than 4. So the number that is greater than 5 from numbers 1 to 6 is plainly number 6. So we do have this one. While for the number less than 4 as our second event, so we do have the numbers 1, 2, 3. So the first event have a single element. So we do have 1 over 6. While the second one We do have 3 elements, so 3 over 6. So we don't have common elements from each set, therefore we're not going to have subtracting value, and this makes our event under mutually exclusive. So no subtracting value, we may now proceed immediately to addition. So 1 over 6 plus 3 over 6, so that gives us 4 over 6, or can be further simplified as 2/3. Okay, so hope you understand how to determine the probability of an event, whether it's mutually exclusive or not mutually exclusive. Let's have another set. Let's have a different experiment. This time, let us talk about spinning a relay containing numbers 1 to 15 now. So from the die, we are plainly dealing with numbers 1 to 6. So let's have add more numbers. So from 1 to 15. Let's have number 1. For number 1, we are asked to get the probability of getting 10 or 13. So there's only one 10 as our first event from a relay, and we just only have 1 13 from a relay. So therefore, nothing is common. So this is under mutually exclusive. 1 over 15. So why is it 1 over 15? Because we're talking about numbers 1 to 15. So there are 15 total possible sample space, or rather 15 total possible outcomes. While for the next one, so we have just only one number, one element, so 1 over 15 as well. So adding these two, so adding these two numbers, so we do have 1 over 15 plus 1 over 15. Therefore, the probability of getting 10 or 13 is 2 over 15. Another one. Probability of getting number less than 7 or greater than 10. So numbers that are greater than 7, less than 7 rather, so our first event. So those are the numbers 1, 2, 3, 4, 5, and 6. While for the second event, greater than 10, so we do have the numbers 11, 12, 13, 14, up to 15 only. Again, we are only talking about numbers 1 to 15 on our experiment. So for letter A, or the first event, so we do have 6 over 15. And for the second event, we do have 5 over 15. So on our sets, nothing is the same. Therefore, we're not going to have a subtracting value. And our event is under mutually exclusive event. So adding now these two, so we do have 6 plus 5, that gives us 11. So 11 over 15. Next example, example number 3. Under this experiment, how about getting a probability of getting a number divisible by 4 or divisible by 3? So the first event is a number divisible by 4. So from numbers 1 to 15, those numbers could be 4, 8, or 12. While for the numbers divisible by 3, those are the numbers 3, 6, 9, 12, and 15. So we add 15 to this one. So therefore, for the first event, we'd have the probability of getting 3 over 15. While for the second event, we'd have the probability of getting 5 over 15. Upon speculating, we do have a common element. We do have a single common element, which is the number 12. Both sets containing number 12, so we're going to have a subtracting value of 1 over 15. So this makes our event in number 3 as under not mutually exclusive event, since they are sharing a common element, meaning we can obtain these two events at the same time. So let us now simplify. First, we add 3 plus 5, that gives us 8 minus 1, so we do have here 7. 7 over 15. Next one. Number 4, probability of getting an odd number or less than 6 odd numbers. So those are the numbers 1, 3, 5, 7, 9, 11, 13, and 15. While for the numbers less than 6, we have the numbers 1, 2, 3, 4, 5. From the first event, our probability of getting a number is 1, 2, 3, 4, 5, 6, 7, 8. So we have here 8 over 15. While for the second event, the probability of getting number less than 6 is 5 over 15. Now, upon looking at the elements from each set, we do have common elements or shared elements. Both of the sets contains 1, both of them do have 3, and both of them do have 5 as well. So there are 3 elements shared by set A and set B, so we're going to have minus 3 over 15. So this makes our number 4 probability under not mutually exclusive event. So 8 over 15 plus 5 over 15 minus 3 over 15. Again, we subtract the common element. So 8 plus 5, that gives us 13 minus 3. So we do have here 15 over, rather 10 over 15. Further simplified as 2 over 3. Next one, that's a more example. Number 5, probability of getting a number multiple of 6 or less than 10. So the numbers that are multiple of 6 for the first event are plainly the numbers 6 and 12. So we're not going to include 18 because we are again talking only the numbers 1 to 15. Then for the numbers less than 10, those are the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So therefore, the first event, they have a probability of 2 over 15. While for the second event, we do have the probability of having 9 over 15. Upon looking, do we have a common element? The answer is yes. Both do have number 6. So therefore, our number 5 probability is again under not mutually exclusive event because they are sharing the same element. So we subtract 1 because only one element is shared by these two sets. So minus 1 over 15. So let us now simplify. First, we add the first two events. 2 plus 9, that gives us 11. Then minus 1. So therefore, the answer is 10. So 10 over 15. Again, we simplify this to the simplest form or 2/3. Let's have last example, last probability for this experiment. Probability of getting composite number or less than 4. Again, composite numbers are numbers that do have more than one possible pairs of factors. So therefore, talking about numbers 1 to 15, the composite numbers present from these numbers are the numbers 4, 6, 8, 9, 10, 12, 14, and 15. So they can be factored more than one pair. So for less than 4, so those are the numbers 1, 2, and 3. So for the first event, the probability of getting composite number is 8. So we do have 8 elements from our set A. 1, 2, 3, 4, 5, 6, 7, 8. So we do have 8 over 15. While for the second set or second event, we do have 3 over 15. Upon looking at the elements, nothing is shared or nothing is common. Therefore, this number 6 is under mutually exclusive. So no subtracting value. So we just simply add these two numbers. So 8 plus 3, that gives us 11 over 15. So cannot be further simplified. So this serves as our final answer. Let's have a different experiment. This time, let us talk about playing cards. So drawing a card from a regular deck of playing cards. So we all know that a regular deck of playing cards contains 52 cards. So this will be our total possible outcomes. So that's problem number 1 or probability number 1. Probability of getting a heart or a black card. So the first event is getting a heart. How many hearts do we have from a regular deck of cards? So we are aware that there is only 13. So 13 over 52. So 13 starting from ace up to king. So we do have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So that's why we do have 13. While for the black card, so we do have 13 pieces for the spade, which is black, and we do have 13 pieces for the clubs or flowers. So 13 plus 13, so we do have 26. So for the second event, getting a black card has a probability of 26 over 52. Now, are we going to have a subtracting value? Is it possible for us to get a heart and a black card in a single draw of card? The answer is no. So we cannot attain these two events at the same time. So therefore, this event is under mutually exclusive. So they cannot happen at the same time. So we just simply add these two. So 13 over 52 plus 26 over 52. So this gives us the answer of 39 over 52. So further simplify this one. So we can further simplify this. So therefore the answer is 3 over 4 or 3/4. Number 2. So under this case, under this experiment, we're not going to list the elements because there are too many. So we need to be familiar with the regular deck of playing cards. For number 2, probability of getting face card as our first event, or an ace. So talking about face cards, how many face cards do we have? So from a card, the face cards are the one that are Jack, Queen, and King. So we do have Jack, Queen, King as the face cards. We are to multiply it by 4 because we do have 4 different suits. So 3 times 4, therefore the probability of getting face card is 12 over 52. For the second one, we do have ace, probability of getting ace. So we do only have ace, then multiplied by 4 because those ace could be a diamond, a spade, a heart, or a club. So we do have 4 over 52. So is it possible for us to get face card or an ace at the same time? The answer is no. So we're not going to have a subtracting value. So we just simply add these two probabilities. So 12 over 52 plus 4 over 52. So that gives us 16 over 52. So then we further simplify this one. So therefore, our final answer will be 4 over 13. Let's have more examples. Probability of getting a number divisible by 3 or a red card. Number divisible by 3. So from a regular deck of playing cards, the numbers that are divisible by 3 are the numbers 3, 6, and 9. Then we are to multiply this by 4 again because we do have 4 different suits from these numbers. So we do have therefore 12 over 52. While for the second one, probability of getting a red card, so the red cards are the diamonds and the heart. Both of these do have 13 pieces each. So 13 plus 13, so we do have 26. Now, is it possible for us to get a number divisible by 3 or a red card? The answer is yes. We can get a number that is divisible by 3 and a red card. The question now is how many are they? So the numbers again divisible by 3 are the numbers 3, 6, and 9. And the red cards that could be divisible by 3 are the diamond and heart. So we do have 3 times 2. So therefore, we are going to have a subtracting value of 6 over 52. So this makes number 3 under not mutually exclusive because we can attain a number divisible by 3 and a red card at the same time. So now we simplify 12 plus 26. That gives us 38 minus 6. So therefore, the answer is 32 over 52. Or further simplified as 8 over 13. So again, number 3 is under not mutually exclusive because we can have both events at the same time in a single draw of card. Number 4, probability of getting a diamond or a J or Jack. So how many diamonds do we have from a regular deck of playing cards? So we do have 13. So 13 over 52. Then the number of J or Jack from a regular deck of playing cards. So we do only have 4. So we do have 4 over 52. So it could be Jack of diamonds, Jack of spades, Jack of hearts, or Jack of clubs. Now, is it possible for us to get a diamond and a Jack at the same time? The answer is yes. So how many cards that are diamond and Jack at the same time? The answer is just only 1. So we are going to have a subtracting value of 1 over 52. Then we simplify now. So 13 plus 4, that is 17. Plus 1, rather minus 1, so that gives us 16. So the answer is 16 over 52, or further simplified as 4 over 13. Let's have 2 more examples. Number 5, probability of getting a club or a flower or a number. So probability of getting a club, so we do have 13 pieces for each suit, so therefore we're going to have 13. 13 over 52. While for the probability of getting a number, so how many numbers are present from a regular deck of cards? So we do have the numbers starting from 2 up to 9. So we do have 2, 3, 4, 5, 6, 7, 8, 9, 10 rather. So we do have 9 pieces of those. So from 2 to 10. Then 9 times 4, because we do have 4 different suits present on a regular deck of playing cards. So therefore, the probability of getting a number is 36 over 52. Now, is there a possibility of getting a club and a number at the same time? The answer is yes. So we do have how many numbers in a club at the same time? There are 9. So we're going to have a subtracting value of 9 over 52. Since there are 9 cards that do contains number and club at the same time. So let us now simplify. So we add first 13 plus 36 giving us 49 minus 9. So that gives us 40 over 52. Or further simplified as 10 over 13. Okay, so hope you are getting how to determine the probability of compound events, specifically under mutually exclusive event or not mutually exclusive event. Let's have the last example. Hope this will be enough for you to understand fully how to deal with these events. So number 6, probability of getting face card or a spade. Number of face cards that we do have. So we do have Jack, Queen, and King. Again, we are to multiply this by 4. So this slip is to be multiplied by 4 because of the 4 suits. So therefore, we are going to have 12 over 52. While for the spade, so we do have 13 pieces for each suits. So 13 over 52. Now, is it possible for us to get a piece card and a spade at the same time? The answer is yes. And how many are they? So the number of piece cards and spade at the same time, there are 3. So we're going to have a subtracting value of 3 over 52. So let us now simplify. The first two we added. So 12 plus 13, that gives us 25 minus 3. So therefore, the answer here is 22 over 52, or further simplified as 11 over 26. Okay? So hope you understand now how to deal with mutually exclusive event. So thank you for watching. See you next time.